Okay, why don't we make a start? It's almost 7:34. So thanks everybody. Can you hear me okay?
Yes.
Yes, no
Yeah, so
problem.
I'll ask people to who aren't speaking to mute, because the way the Zoom works is whoever makes the last noise gets highlighted in the speaker screen. So when uh, if you're going to speak, then you can unmute yourself, but otherwise it'd be nice if you mute. And I do worry sometimes when we haven't actually gone online for weather very often, but I worry about whether someone might be standing outside C2045, but I don't think that's going to happen tonight because MUN is closed. So I'll go to we have, I see 20 people online, so and some people are 21 now, and some people are more than one per screen. So great to see everybody. And so I'll start with an acknowledgement. We acknowledge that the lands on which members of the St. John Center of the RASC live and pursue our hobby are situated in the traditional territories of diverse Indigenous groups. We acknowledge with respect the diverse histories and cultures of the Beothuk, Mi'kmaq, Innu, and Inuit of this province. And I'll just go back to the agenda. I would have been last month when Ezekiel gave his talk, we had a speaker's gift for him, but because of Randy's situation, we couldn't get it that week. So the plan was to present it today, but it's still coming. So don't give up hope, Ezekiel. There's something coming. I'll say a bit about the AstroImaging contest. We're going to hear from Chris, and I'll say a bit more when that comes up. And Crater of the Month, I've got in quotation marks. It's going to be Gary again, because it's actually Lunar Feature of the Month, and maybe it's time to change the name of that feature, but there we are. So I don't know if we have any visitors. I think I recognize most people here, but I'll just point out we meet at the third Wednesday of every month, except July and August. We're a supportive community for people to learn about astronomy. Tell your friends. One of the benefits of membership is the RASC NL Talk, and there's lots of shared information, discussion, mentorship on there. And so there are benefits to membership. And so some announcements. Our next meeting is going to be Wednesday, March 18th. It's going to be a members meeting, so people are invited to share a short talk about a project, a discovery, new equipment, something you're learning. So far, Jim has volunteered to talk about adapting an old Nikon lens for new multi-narrowband imaging, Jim Stacy, and there's been some talk about having some discussion about the different kinds of smart scopes, because we're starting to get quite a bit of variety in the group. I'll point out that March 10th, there's level 1 stellarium training for RASC Atlantic members. You do need to register, and you need to register soon so they know you're there. And there is a link here. If you need that link, get in touch with me or Randy, and we'll get that to you. Once you register, you'll get a confirmation. We don't have many details yet, but the RASC General Assembly, I'm sure it'll be online, will be May 2nd and 3rd. And as many of you may have seen in one of the messages that was sent out, the executive director for the RASC, Jenna Hind, is leaving, and so there's a job there if somebody wants it. But I suspect at the General Assembly there'll be some recognition of her. I would hope so. The Terra Nova Dark Sky Festival, it's it's been rebranded from just Night Sky Celebration. It's now going to start on the Thursday night. It's the week before Butterpot Star Party, and it's different from the date on the RASC calendar. So watch for that. They're talking about something like an astronomy on tap event, an invited speaker, a night walk, plus the normal things that happen, maybe an outdoor movie. You can contact me or Doug Grushi, or just indicate your interest on RASC, and I'll talk. And I have heard from a few people about that. Thanks for responding. I checked today. There are still a few service sites for Friday and Saturday. I don't know about Thursday night. I suspect the Authentics are pretty much booked for that weekend, as far as I could tell. So, but these things change as you get into the season. The imaging contest, I haven't actually checked in the last few days, but I don't think there's many images in yet. The submission deadline is March 31st, so I suspect I'll see a lot on March 29th. We've got 4 categories. They need to be a new image for this, well, not in the previous contest. The obvious information to include, you send it to photos@stjohnsrasc.ca. The judging will be in May, and it'll be by a Google poll. And Jim Johnson has scared up awards, very generous contributions from Hibernian Management and Development, Ontario Telescope, Astronomy Plus, and David Astro. And I think that's the list so far, right, Jim? Anyways, I think that, yeah.
Correct.
Okay. So, with no further ado, this is, it's my great pleasure to introduce Chris Stevenson. This is actually sort of an extension of our 60th anniversary. I think that should actually say February 66, right?
I think so, yeah.
Yeah, so Chris's father gave one of the first talks, and it to the center. It was on spectroscopy, and I think it was almost, Randy can correct me on this because I think he's been counting on his fingers, but I think it's pretty close to 60 years to the day, right?
Yes, it was. And it was February 66. And it was the very first lecture to the center as a center.
Right. So the first one after the center had become official.
Yep.
So Chris, of course, has studied spectroscopy. And so he's going to bring us up to date and maybe give us a few memories at the same time. So I'm going to stop sharing and invite Chris to start sharing. So you ready to go, Chris?
Sure. Thanks, Mike.
Okay.
Sharing.
All yours.
Entire screen. Share. Oops.
Okay, we're seeing, there we are. Looks good.
Can people see that?
Yes.
Okay. Thank you. Yeah, it's pretty weird. I hope this is not the last talk to the center as a center. Sorry, I had to say that. I hope we'll keep sailing on. So, in any case, thanks very much. Yes, I spent a lot of time doing astronomy. Grew up, my father was there he is, Carl Stevenson. Can people see my mouse? Yes.
Yes, we see your mouse.
Yep, good. Also a master's student of physics, one of the first crop of master's students in MUN physics. Grew up around telescope making stuff in the basement and a rickety 6-inch homemade telescope, etc. And you know what? I couldn't help but get into astronomy and physics myself. So I had no idea what he talked about then because I was extremely young. And however, it made perfect sense to follow up 60 years later to the almost to the day. I'm just going to try and turn off the display of row characters on the right-hand side. There you go. Perfect. Okay, let's get going. I've got 30 or so minutes to do this, and there are more slides than I wanted. So here we go. Spectroscopy. Astronomy is a field where we study distant objects in the universe simply by looking at them. We cannot touch them. You look up in the night sky and you see stars, and they're just points of light. And so how do you make sense of that? We know stars now as, giant balls of hot gas, and nuclear fusion powers them, and this, that, and everything else. How do we get there? The only thing we can do is study the light we see from stars and other objects. And for stars, they have no size. So you are left to teasing apart that light into whatever else other information it contains. Light's made of wavelengths, so you do spectroscopy with the light and to find out what other information is encoded in there. So spectroscopy is central to astronomy. This is an image of Webb telescope's first deep field, I believe. Humans have inadvertently been doing spectroscopy of sunlight anyway since the beginning. Anytime there's rain or high altitude ice crystals, you get sundogs and halos and all this lovely phenomena which break sunlight into colors. And even my wife Sandra photographed a marvelous rainbow from outside of her school in the West End. And I think I showed that to the center a few months ago. This was last November. Just a neat spoiler here, the secondary rainbow, the colors are reversed from the primary. So just given that there are concepts in this that I think I should explain, let's go through a short list of them. First of all, what is light? Light can be thought of as photons, particles of light, or also be thought of as waves with a speed and a frequency, a wavelength. And that speed is famously the speed of light, which is invariant, and it's been defined a number of years ago, actually defined as a physical constant. So hence all the digits. Those are real. It's speed of light in a vacuum. Electrons emit photons. Electrons have a certain amount of energy when they're in an atom. And, okay, sorry. The relationship between energy and frequency for a photon. Energy is frequency times a constant called Planck's constant. And the wavelength of is just waves are moving past an observer, a certain number of them per second, that's their frequency, and the wavelength is going to set the frequency based on the speed. So there's a relationship. E is F, the frequency, times a constant, or C over lambda times a constant. C is the speed of light. There are a few formulas in this talk. None of them are more complicated than A equals B over C. Photons can have any wavelength at all, which is kind of scary. Photons can have wavelengths ranging all the way from kilometer scale even. I think the very, very longest wavelengths can't get to the ground. But wavelengths with wavelengths from meters to millimeters certainly can. And there's a famous millimeter telescope in Chile, the Atacama millimeter array. That's on the ground, so it's looking at millimeters. Then most of the light's blocked out. Then we can see visible light on the ground, and then everything else is blocked out. Light wavelengths can be as short as the size of atoms, atomic nuclei, in which case they're ultra high energy gamma rays, packing a lot of energy, too much energy to hit the atmosphere and not do crazy things. Visible light gets to the ground. We see visible light with our eyes. So do other creatures. We all evolved to see visible light. Human beings are what's called trichromic. We can see three fundamental colors with receptors in our retinas. We see blue light at 400 nanometers, 400 billionths of a meter is the wavelength for blue light. Green is 550, red is 700. Pigeons, I understand, can see 4. Snapping shrimp can see 21 or something, 33, and it's crazy. So the rest of this talk will be limited to visible light and near infrared light, maybe. And the interesting question, since radio gets to the ground, is there anything that can see radio? You have to be very big. More basics. I won't dwell on this because it'll take too much time. Consider the simplest element in the universe, which is hydrogen, which makes up 90% of the universe. It has one electron, and that one electron, when it's bound to a nucleus, can only have very specific energies. And the reason I'm going through this is it's an important concept. The fact that the energies are very specific means that when the electron, either the atom absorbs energy from outside or releases energy in relaxing from inside, the energy that it's absorbed or releases is very specific. So the photons that are released or absorbed have a very specific energy or a very specific wavelength. If you were masochistic, you could use a formula on the bottom and calculate the wavelengths of all those lines for hydrogen because it's so simple. For any other element, it's a bit more involved. But the upshot is every chemical element with a different number of electrons and different size nucleus has a different set of emitted lines, and only these emitted lines. Everything in between this color and that color, this is hydrogen alpha in red, red hydrogen alpha. We have a hydrogen alpha telescope that shows the sun in red for this reason. There's hydrogen beta, you'll hear that a few times. Other elements, sodium, there's a famous sodium D lines, a pair of them there. Helium, neon, mercury, every element has a set of fingerprints. This allows us to use spectroscopy to figure out what's in objects that we're looking at. That's a powerful idea. Another powerful idea, when we look at stars, they have an overall color. And some are blue, white, some are red, orange, etc. That's a clue to their temperature. Thin gas, like in a neon tube or a hydrogen tube, emits those fingerprint lines, but more solid things like a hot brick or a dense ball of gas that's a star, the photosphere of a star, emit what's called black body radiation. And black body radiation comes out of the brightness versus wavelength has a specific shape called Planck curve. And you can scale the Planck curve. It's the same curve, but you can scale it with temperature. And the height goes up at higher temperatures. And it's sort of, the peak goes to shorter wavelengths at higher temperatures. But there's a very simple relationship for finding, very simple relationship for finding the temperature of a black body. And you simply measure where, what color, what wavelength the peak emission is. And you divide a constant by it. Oh, sorry, you measure the wavelength, and that wavelength is going to be a constant divided by the temperature. Very simple. The sun's surface temperature is something of the order of 5,500 kelvins. Kelvin's about the same size as a degree Celsius, so it's 5,500 degrees Celsius or so. So a spectrograph is required to break up white light into its colors with more control than, say, raindrops in a rainbow. And a spectrometer would be a spectrograph with something at the output end to record your spectrum. If you're using your eye, then the ensemble is called a spectroscope. The heart is a dispersing element, something that'll take the input white light, say, and spread it out into its colors. And a prism is a classic dispersing element. It turns out the speed of light in transparent solids varies slightly with wavelength, and higher energy photons actually have a harder time getting through transparent solids, so they travel a bit more slowly than lower frequency ones. In this animation, you can see the violet lines are slowed a little slower than the red ones, and so the two come out at different angles. The prism disperses the light into colors. So here's a fun picture that my wife gave me last month. Sir Isaac Newton, who played with prisms, working on the Pink Floyd album cover, Dark Side of the Moon, in 1665. How very prescient of him. Isaac Newton used prisms to show that all the colors of the rainbow were contained in white light. If you use a second prism, you can take the rainbow and shove it back into white light. That's sort of the ultimate proof. As an aside, here's the actual album cover based on by Storm Thorgerson did the artwork based on a photo in a 1963 physics text. It's actually fairly accurate. Pink Floyd's album came out after Dad's talk. Pity. I'm sure Dad was familiar with it, though. I have to mention this, though. The dark side of the moon, any amateur astronomer should bristle because, of course, any body rotating in sunlight like the Earth or the moon takes a day for the Earth, takes a month for the moon. All sides are at some point dark and all sides are at some point day. You might want to say the far moon, not the dark side of the moon. The dark side of the moon was facing us yesterday. It was new moon. I believe there was a annular solar eclipse somewhere. So that's a prism. Because light's also a wave, it can be made to interfere with itself if you force that wave to go through a periodic, evenly spaced series of holes, or reflect off a periodic series of slats or mirrors, and what comes off will interfere with itself, and you'll only see light in particular directions for a given wavelength and groove spacing. These are diffraction gratings. They come in two kinds, reflective and transmissive. A transmissive diffraction grating example would be the rainbow glasses you can buy in dollar stores and things. A very famous equation, I'll just mention it. Alpha angle in, beta angle out. It's all geometry, hence the trigonometry. Okay, I lied. I said there'd only be A equals B over C. It's not hard. It's just pure geometry. There is one interesting difference between gratings and prisms. There are few, of course, but prisms have a non-linear dispersion. The way the colors are spread out varies with the difference between this pair of wavelengths and that pair of wavelengths. For gratings, it's linear. That's great because then it's a very predictable and easy to work with thing. The other difference is that they're kind of backwards. In prisms, violet light bends more than red. For gratings, red light bends more than violet. Prisms also take all of the light that goes into them and spits it out in one spectrum. So they're quite efficient. Gratings will generate many orders of output. And you have to angle those little facets, if it's mirrors, so that you get a specular reflection in a given direction. That's called blazing, and that's how you make a grating behave a bit more efficiently. Otherwise, they're actually not that efficient. Spectrographs. Technically, when you build a spectrograph, you have at the back end of your telescope, and you want the light that goes through the dispersing element, every ray of light, if you will, to be parallel to every other ray. So the angles are all bundled, they make sense. If it was all random going in, it'd be random coming out. So you want to collimate the light coming in. Normally, you have a slit that like a line image, a very narrow gap. You focus your telescope image on the slit. The light that comes through that slit is picked up by either a lens or mirror at the focal length of that lens or mirror from the slit, and the light that comes out of that is pretty much parallel. And then you stick it through your prism or transmission grating, or reflect it off your reflection grating, and then you have a camera to pick up the dispersed light and refocus it back down to an image of the slit, but one image for every wavelength in the light that was behind the slit in the first place. And we can use CCD cameras and CMOS cameras these days, which are very sensitive instead of our eyes. Here's a graphic. The top one has a collimating mirror and a camera mirror. This is a reflection grating. Here's your detector. So there's three optical elements. But if you are very crafty and clever, and they can do this now, you can make a concave holographic grating, which has all the aberrations that you create, all the image destroying weirdness that would happen if you try to do this, corrected, you can actually form a clean image of the entrance slit off of this one optical surface dispersed into a spectrum on an array. That's amazing. I have a couple of these things. They're not cheap, but they are amazing. I'm playing with them, and I'll keep you up to date on how they work. So back to basics again. Any talk on spectroscopy would be remiss if they didn't mention the three laws of spectroscopy. Gustav Kirchhoff, in the 1845, 1840s, worked with Bunsen, who invented the Bunsen burner to get a handle on spectroscopic basics. So he came up with these three laws. One, a black body, a black body emits a black body spectrum, a continuous spectrum characteristic of its temperature. Two, a thin excited gas, like the neon in a neon tube or the hydrogen in a nebula, will emit an emission spectrum. A few discrete lines on black. That's characteristic of each element. That's doing the emitting. Three, if you have that gas sitting in front of a black body, it will absorb out those very same wavelengths, and you have what survives the absorption process, an absorption spectrum. The three laws of spectroscopy by Gustav Kirchhoff. There he is there. Here's a graphic I hauled out of a online video by Anush person, anyway, decoding starlight. It's on YouTube. And afterwards, I realized those are really wonky prisms. These prisms are doing things that prisms can't do, but just pretend that they're oriented properly. So here's our black body. In this case, it's an old-fashioned incandescent light bulb, which has a very hot tungsten filament in it. And here's our gas cloud. Here's our absorption spectrum, because the gas is absorbing out wavelengths. These are the wavelengths of hydrogen, it turns out, H alpha, beta, gamma, delta. Here's H alpha, beta, gamma, etc. When you look at that gas cloud from the side, because it's excited by this and it's emitting those lights, those lines to the side, you're looking past the cloud, not at the black body. The black body itself, of course, continuous spectrum. Forgive the goofy prisms. So stellar spectra are usually absorption spectra of their atmospheres with a hot photosphere below the atmosphere emitting a continuous spectrum, a black body spectrum. So when you see a star's spectrum, what you're seeing is a spectrum of its atmosphere, where that gas thins out. So ostensibly, it's the same composition as the body of the star. Joseph von Fraunhofer first turned a early spectroscope to the sun. Hopefully he didn't look through it and projected it or something, and saw these black lines in the solar spectrum. The sun is a star, and at the time, not knowing what the elements were producing the lines, which lines were produced by which element, he simply assigned letters. That's all he could do. Now we know better. D, for example, was used for the famous sodium D lines, that pair of yellow lines. In the Fraunhofer line, C is nothing more than H alpha. E is a line due to green, a line due to iron. F is H beta, H and K, that's the famous H and K calcium line pair, and so on. The sun spectrum seen by Fraunhofer. So you might be tempted to say, okay, the sun is mostly hydrogen and a little bit of helium, and so the spectrum you should see from the sun or any other star should be mostly hydrogen, a little bit of helium, and the traces of anything else in it will be totally swamped by those materials. Not so. As we saw from the Fraunhofer lines, in fact, iron, magnesium, sodium are actually quite prominent. This led people of the day in the early 20th century to conclude that, stars are literally hot embers of stuff glowing at high temperature, and iron and hydrogen, helium are just a small proportion of them. Cecilia Payne-Kapushkin, whose PhD supervisor was Henry Norris Russell, who actually, and he didn't agree with this initially. She pointed out that no. It's not how much stuff is in the gas. Stars are, in fact, hydrogen and helium. It's the temperature of that gas that decides what you see. So at a particular temperature, hydrogen lines are going to be most prominent in that absorption spectrum. At another temperature, you might see ionized helium lines. At a lower temperature, you might see ionized calcium lines. So and I'm not going to go into the details of this because they can get complicated fast. Good for her. They eventually believed her. Very busy image. We know stars have multiple spectral types, and that basically is a temperature sequence. O stars are very hot. M stars are very cool. Cool stars have more molecular band lines and all these busy black lines and so on. But for example, here are hydrogen lines. They really only are seen in A stars. All these stars are mostly hydrogens. Where are the hydrogen lines for G stars? Our sun's a G star. The hydrogen lines are there, but they're weak. An easier way, especially for people studying this, is just to simply plot brightness on the vertical axis and against wavelength on the horizontal, or flux, normalized flux, the energy per square area received at Earth. And this is what stellar spectroscopists are familiar with. So same sequence, O stars on top, M stars on bottom, and you can see the differences between them much more clearly. I am not going to go into our familiar OB, AF, GKM or anything else. That's a talk for another time. Again, A stars show a hydrogen most prominently, but not less prominently for all the others. I like nebular spectroscopy. So I have to talk about nebular spectroscopy. Sir William Huggins, who is an amateur, and his wife built an observatory in their backyard in Tulsa Hill, London, UK in the mid-19th century, and they observed anything they could in the sky with a homemade 2-prism spectroscope on 5 and 8-inch refractors. There's the spectroscope in the middle. Nevertheless, Huggins was the first to properly distinguish between nebulae. Everything was called nebulae. Nebulous just meant fuzzy. But the Orion Nebula and a few other things similar to it actually looked like gaseous things. And in fact, they emit, he saw, emission line spectra, like you would from a neon tube, those fingerprints. Other fuzzies, like the Spiral Nebula, showed to have a stellar spectra, continua with dark lines missing, the spectra of stars. He was distinguishing between true nebulae and what would go on to become known as external galaxies. In about a century before I was born, within a few days actually, quite neat, 1864, August, and I was born in August of 1964, he was looking at the Cat's Eye Nebula, NGC 6543, easy to remember, and a planetary nebula, we now know, a sun-like star that dies and in the process of dying throws off the gas in its outer atmosphere, and the inner part becomes a white dwarf, very hot, makes all that gas glow. And so it is excited, glowing, thin gas. So it has an emission line spectrum. And he saw the lines of hydrogen and helium, but really, and also a very, very bright line, blue-green line next to H beta that he didn't know at all. Nobody knew this at all. He said, what on earth is this? Well, it's not on Earth. Maybe it's an element called nebulium that's out in the universe and it doesn't exist on Earth. He actually submitted a letter to a journal about that. Nebulium. People actually believed it for over half a century. In 1927, astrophysicist Ira Bowen, that's a very familiar name to anyone who does this, showed how Huggins nebulian lines were actually emission lines from doubly ionized oxygen. Only they've never been observed before because these are what are called collisionally excited lines, oxygen bumping into each other and their electrons being slightly excited, very, very tenuous. And if those ions hit the wall of a glass container, they would be de-excited before they got a chance to emit light. That doesn't happen in the expanse of near vacuum space in a nebula. So we see forbidden lines from nebulae actually rather well. Here's a spectrum I took of the Orion Nebula a bunch of years ago with a prototype spectrograph, and I labeled the lines. So here are those O3 lines. Here's H beta, H gamma. There's H alpha sandwiched between N3. But most people taking hydrogen images don't realize they're also taking nitrogen images. Here's argon 3, here's a helium line, and so on. Again, the thing to note here is the forbidden lines of things like nitrogen are actually very bright, even though there's not nearly as much nitrogen as there is hydrogen in a nebula. Again, they're particular dynamics. But the idea is we can see what's in the material making up nebulae and stars. Incidentally, these things are, with advances in technology, a century later, put a CCD on the back of your telescope, a small telescope, and you can take spectra of all of these brighter things rather easily. Here's an example from Jim Ferreira in Livermore, California. Again, this is done with, I think, a 9¼ inch SCT, a Schmidt-Cassegrain telescope, backyard telescope. The final basics, dynamics. Okay, it's nice to measure temperature and composition, but we want to know how things are moving around up there. We want to know physics. We want to know the dynamics for systems, because things orbit a system, and those orbital speeds are related to masses. We can learn masses. You can learn all sorts of things. The key to this is the Doppler effect. We only have motion along the line of sight to work with because we can't step to one side and look at this object from one side. We can only have the line of sight, but it's a very simple relationship, and it's essentially we know this from fire trucks and ambulances rushing at us and then passing us, and the pitch will drop as it goes by, and the waves get stretched out, and that's a very simple relationship with the velocity of the source and the velocity of the waves, and you're assumed to be a stationary observer. And it's just basically a key part of the equation is the ratio of the velocity of the source over the velocity of the waves. 1 plus that times the wavelength of the waves when you're standing still is the wavelength they appear to have, which is different because of the velocity. Radial velocities, we call these radial velocities because it's a radius. Okay. Looking at stars in our own Milky Way, the radial velocities to Milky Way stars are typically tends to, at most, plus or minus 300 kilometers a second. Towards our way, we're only looking at one component. There are other components to the side, but if you look at enough stars, you get a feel for, their motions are random. You get a feel this is the velocity of the star in the galaxy, tends to 300, at most about 300 kilometers a second. Light is 300,000 kilometers a second, so that's a small fraction. Doppler shifts for when you're measuring radial velocities are small. Here, 30 kilometers a second is only 0.05 nanometers. So the shift is quite small. Similarly, Cepheid variable stars are pulsating variables, and they breathe in and out and in and out. They actually pulsate in radial pulsators. And you can measure that velocity towards you and away from you. And that's also 30 to 60 kilometers a second or so. And so you need a spectrograph that's capable of measuring those small shifts very well. So you need a higher resolution spectrograph. Here's a situation. You look up at the star, a star in the sky, and it looks like a point, but it's actually two stars orbiting one another. They're too close together, they're too far away that you can tell them from anything other than a single point. And the further away they are, the more hopeless it is that you'll ever resolve them as anything more than a point. But if you take their spectrum over time, I'll reset that animation. As one goes around the other, they're both orbiting their center of gravity, this little red dot in the middle, and you can see the lines the GIF wasn't made with with loop involved. You can see the lines from the two stars alternately red shifting and blue shifting. That tells you a lot. For a moment, you can see each individual star to the spectra from the two stars interwoven, so you can untangle them one from another, and you can tell what each star is. And you know how bright they are. You can sort of figure out how far away they are. Blah blah blah. You can fill in a lot of the boxes. You can get their mass ratio. So you're getting at masses, all from doing spectroscopy, all by measuring radial velocities. But in this case, radial velocities redshifting alternating to produce this interweaving back and forth motion, which tells you about the orbit of these two stars that appear to be a single pinpoint otherwise. I was reminded that Alcor and Mizar in the Handle Big Dipper, the famous binary pair used to test eyesight by some people, are actually gravitationally bound. They are a real binary star. Mizar is itself another binary, and Mizar A, the brighter component, is of that other binary, is itself a spectroscopic binary. And here's the light of Mizar A seen at two different times, and you can see here the spectra are all overlapping, and here the two star spectra are slightly separated. In order to measure these and even higher or smaller shifts, we'd like to get down to a kilometer per second, or even better for other things. Very high resolution spectrographs are required. You could use interferometers. What's an interferometer? You know what? I'm not going to go into that. Ways of making very high resolution spectrographs, huge prisms with thousands and thousands of lines per millimeter, multiple prisms. You saw Huggins' spectroscope had two prisms in it, not one. There's a clever trick whereby you can have a special kind of diffraction grating called an échelle grating. Échelle is French for staircase. These things are used at very high incidence angles, and they're designed to put the light deliberately into many, many, many orders, all of them almost equally bright. And then you sort those orders out in the opposite direction on an imaging chip with a prism. Bit more complicated. Here's a design by an amateur who's actually built it and it works. Here's when you use a professional échelle spectrometer on Procyon, you can stretch its spectrum out. Here, I don't know, there's 30 odd slices here, and every one is detailed. This is the sodium D line right here. The distance between this and this is only 0.6 nanometers. And in fact, the lines that are fat and fuzzy have a shape. Stellar spectroscopists study line shape. That's very important for measuring stellar gravities and a bunch of other things. In fact, you need a high resolution spectrograph to do a decent job of astrophysics, stellar astrophysics, and so on. Right, moving on. So stuff that Dad didn't know about in his talk. Exoplanets were the stuff of Star Trek. Star Trek, I think, was just coming out in 1966, traveling to other planets. There was absolutely no evidence of any planets around any other star. It was total science fiction. Exoplanets are a modern reality, and most stars have them. So how were they found? The very first exoplanet was discovered not around a regular star, but around a pulsar PSR B1257 plus 12. That tells you it's at 12 hours, 57 minutes of red ascension and plus 12 degrees declination. That's how we name things. But anyway, 2,300 light years away. So forget trying to see anything other than a dot of light. And they did this by noting very periodic timing irregularities in the train of pulses you get from pulsars. In effect, the Doppler effect. The pulsar was being dragged around periodically by something orbiting it, the gravity of something orbiting it. Remember the binary star, the two stars orbit their common center of gravity. In this case, the pulsar and the planet are orbiting their center of gravity. The pulsar is itself moving very slightly. You can measure that. They did. If you can measure radial velocities to mere meters a second, now you're talking. You can do all kinds of things. That's a high order task. Here's a star 18 Delphi B, the exoplanet. And the radial velocity curve for this, plus or minus, what, 100 meters per second. That's actually relatively easy for this sort of game. The sun wobbles because of Jupiter orbiting it by only plus or minus 9 meters a second. So if you wanted to determine Jupiters around sun-like planets, sun-like stars, using radial velocities, that's what you're up against. But people are doing it. There are hundreds and hundreds that have been detected this way. So, on the other end of the spectrum, large shifts. In 1923, Hubble famously discovered a Cepheid variable in M30. I have a very particular period of time over which they change by a very specific amount of light. Sorry, I just got a warning that says my connection is unstable. I hope people can hear me. Thus, you could look at the apparent brightness of the Cepheid and figure out how far away it is. He found out how far away the Andromeda Nebula was, and it turned out to be millions of light years, a couple of million light years, well outside of our own Milky Way galaxy. Thus, cosmology took a huge step, and all those fuzzy nebulae, spiral nebulae, and others were external galaxies. He then took spectra of as many of these fuzzy external galaxies as he could. Remember, they show continua with the black absorption lines in them, like stars, and pretty much the same pattern in any given galaxy statistics. But the further away the galaxy appeared to be, the more shifted the pattern of lines was. And this is the velocity distance relation called Hubble's law. Here's the plot of the original one from his original data. The Hubble constant h0 has changed over the years, and it's something approximately 70 megaparsecs per, that's the idea. Observational cosmology was born, very large. Other people were measuring galaxy velocities as well. Fritz Zwicky in 1933 measured the radial velocities to galaxies in the Virgo cluster, and he found that they were buzzing around faster than they should for the amount of matter that they seemed to contain, based solely on the starlight they were emitting. If you thought that the mass of stars was emitting all the light, well, that's not enough mass. The cluster should explode apart. In fact, it's still held together. So he came up with a Dunkelmaterie, dark matter, literally. He coined the term in 1933. I think people thought he was a crackpot. He was described a self-described curmudgeon and a lone wolf. But he would get his day later on. And for an admitted curmudgeon, his birthday is Valentine's Day, actually, so he can't be all that bad. So in the 1970s, Dad would have known about Zwicky, but I doubt very much he talked about Zwicky's dark matter. In the 1970s, after Dad's talk, Vera Rubin looked at the rotational curves of galaxies, like M31 pictured here, exhaustively, taking radial velocity measurements of points in the galaxy at different radii and plotting a graph. And you can see here that the galaxies don't rotate as vinyl records or solid disks. They rotate differentially, but you always expect that as you get further and further away from where most of the mass is, based on the light, the velocities will drop off because you don't need to go so fast to stay in orbit. Well, in reality, the curves always flatten out at a non-zero value. There's extra mass somewhere here, lots of it. In fact, much more than the visible mass you can see. Because of Vera Rubin's work, the term dark matter was revived and became popular. We don't understand 4/5 of the universe. What's going on? They named the new 8.4 meter Large Synoptic Survey Telescope in Cerro Passion, Chile. There's a new big telescope designed to photograph the sky, the whole sky, every couple of nights at high detail and high resolution, using the world's biggest CCD camera. Here's a model of it here. They named this the telescope after it. This telescope doesn't do spectroscopy that I'm aware of, but it discovers lots and lots and lots of things that you can analyze with spectroscopy afterwards. So quasars. Speaking of big shifts, Dad's talk was done just a couple of years after Martin Schmidt, an astronomer, used the 200-inch Hale telescope to photograph the quasar 3C273, and that's the nearest, brightest quasar. Near is a relative, though, because when he took the spectrum of it and went through the Doppler shift, he got a redshift of 0.16158, and that, using the Hubble constant of the day, put this at about 2 billion light years away, easily the furthest thing observed at the time. This put Martin Schmidt on the cover of Time magazine. This is a magazine I grew up with. We always had an issue of Time sitting on the coffee table, always, up until the 1990s, up until I left to go to Toronto. Here's a modern photograph of 3C273 by the Hubble Space Telescope, and we now know quasars to be supermassive black holes in the centers of most galaxies, but in the earlier universe, things were closer together than supermassive black holes. There were more interactions, matter was falling into them. You get a bright accretion disk, lots and lots and lots, very bright accretion disk. That's the reason they're so luminous, and it can be seen over cosmic distances. And you sometimes get jets. Here's a jet for 3C273. M87 in Virgo is a much nearer and somewhat quieter example of a quasar, but you can see the galaxy around it rather easily. Quick note about quasars. Back in the 70s and so on, people were studying them, taking spectra of them. It was noticed that you get this bright line of which is from hydrogen, called Lyman alpha. The Balmer series, H beta, H alpha, so those are the visible lines. The ultraviolet series is the Lyman series, and Lyman alpha is at 121.6 nanometers. So we see it here from quasars in emission, and then we see copies of it, little ones, in absorption all the way through at many different redshifts. These two spectra have been shifted to zero velocity. So Lyman alpha appears to be, in emission, appears to be at 121.6. Here's 3C273, which is nearby. Not too many gas clouds between us and it, over 2 billion light years. Here's Q1422 plus 2309. And notice the redshift is way larger. It's a redshift of 3.6. So this is many more billions of light years away, many more clouds to look through, many more Lyman alpha lines in absorption. The Lyman alpha forest is a term. So these days, again, with amateurs, fast forward, 60 years, and you can go out and you can buy this star analyzer thingy, which is just a transmission, 100 groove per millimeter transmission grating. You can thread it onto the end of your camera, stick it in your telescope, and expose for a couple of hours. And this is 3C273. And they even got the redshift right. Good for them. Stargazing.net, David, spectroscopy, 3C273. So part of me bristles at taking a grating and just screwing it onto your camera in the converging beam of a telescope. But if the beam is slow, you can think of it as almost parallel. I tried this myself on Campbell's hydrogen star. It works. In my case, I didn't buy the thread-on filter. I had a flat demonstration 100 grating, line per millimeter grating kicking around. I made a plywood adapter and stuck it in at the end. It worked. Here's Campbell's hydrogen star. This is a 0th order image. Remember, it's a grating, so there's a 0th order. And here's H beta, here's H alpha. And that dark part here is an atmospheric band due to Earth's oxygen. Almost at the end. I thank you for your patience. So things have changed a lot since 1966, but they really changed in 2020 2021, Christmas 2021, we launched the Webb Space Telescope, a telescope larger than the Hale 200-inch, and it was put out to beyond the moon at the second Lagrange point, which is a gravitational balance point between the moon and the Earth. So you put things at the second Lagrange point, and they'll just sort of sit there because they're tugged on equally. So it's an equilibrium point. It's designed to observe the early universe, where everything is highly redshifted. So it was designed to deal primarily with near-infrared and infrared light. Its mirror is gold for that reason. Gold's a very, very good reflector of infrared light. To put into perspective how far we've come since Schmidt's 1963 Hale observation of 3C273, which you can do with a backyard telescope now, here's a Webb image from just last month of MOM Z14. Z14 means the redshift is 14. This is only 200 million years after the Big Bang. In fact, Webb's big thing in the last couple of years has been it's seeing fully formed, we think, nearly fully formed galaxies way too early in the universe's history. And this is forcing a big rethink as to our ideas about the formation of the universe. And again, Webb has a bunch of instruments on it, a bunch of spectroscopes. In fact, the Webb's near-infrared spectrograph, which I believe was designed and built in coordination with Montreal, can now take the transmission spectra of exoplanet atmospheres when they're transiting in front of their stars. That is mind-blowing. That's a spectacularly difficult thing to do, but Webb can do it. So here you see sodium features and water features, a carbon monoxide feature, carbon dioxide, sulfur dioxide. We can actually measure the components of exoplanet atmospheres now. This is simply astounding. Dad would be very impressed at this. I've gone on long enough. Thank you very much. It's probably enough. And I'll pass it back now to Mike.
Okay, well, I invite everybody to unmute and show Chris our appreciation. Or at least you can hear our appreciation.
Thank
Great
you. Can you hear
talk,
me?
Chris.
Great job, Chris.
Lots of information, and I loved how you sort of tied it back into your father's stuff and the sort of history. I'm sure we've got a couple minutes for questions. Anybody, you can sort of indicate or just unmute and ask a question. I guess we're not too formal here. If not, I do have a sort of question / comment, more comment.
Too long.
What's that?
No, never mind. Too long would be the comment.
No, it was fine.
Okay.
So it occurred to me while you were going through, and your father did his MSc, and I don't know who his supervisor was, but I think I might be able to guess. I'm Memorial. One of our departed colleagues was Dr. Reddy, and what he did was essentially, it was called laboratory astrophysics because he would do high pressure cells with exotic molecular ions and find the spectra, and then observational astrophysicists could use that to identify things. Was your father involved with that?
Oh yeah. I do remember Dad talking about how Patty would smoke like a chimney, and they had all these high pressure nitrous oxide cells. Meanwhile, he was smoking in the lab with ignition sources. It's astoundingly funny.
Yes, I do remember a stainless steel cylinder being embedded in a ceiling in one of his labs at some point, but
I
don't think that was because of smoking.
Again, I was very young. Yes.
Okay.
Unbelievable. Cho was Dad's other.
Oh, of course, yeah.
supervisor.
But same sort of stuff, yeah.
Yeah, I think actually one of them, I think it was Patty, was actually my godfather.
Okay.
Believe it or not, because I came on the scene while Dad was doing his studies. So anyway,
Okay.
thanks, Dad, and thank you, everybody. And
Okay. Well,
I hope
let's
from
let's
somewhere you
thank
saw
Chris
that talk.
again.
Okay.
Chris, I
Yeah.
just got an email from Tom Field because you were just mentioning our Spectrum, and he's just upgraded his program again.
Who?
Tom Field, our Spectrum.
Oh, yes. Okay.
Yeah, he's just upgraded his program to include a
Okay.
few more things. So I still use
Oh,
that.
yes. Yeah. I've haven't played with it that much, but I may look at it again. That's great.
Okay. Well, thanks
I have a
again.
question for Chris.
Oh, go ahead.
Just wondering
Yes.
how do you get the spectra from the really faint stars? I know, like you said, the web they can do it, but just normal guys like how do you really faint stars? How do you get the spectra from that? I just wondering how you do that.
Well, okay. I never spectroscopy is taking the light that normally ends up in a point, we'll say for stars, and spreads it out over as many pixels as you want your spectrum to. You design your instrument, whatever. So uh, you're diluting that light by a factor of 1,000 or so. So it's a tall order. If you're going to start by doing spectroscopy of faint things, you need a larger telescope or a very, very, very sensitive camera. Fortunately, all our cameras these days are extremely sensitive. They are, if you look at the read noise of your chips, they're all single electron read noise. These are little miracles. Only a decade or two ago, these things would be extremely expensive scientific equipment. Now we've got all of them kicking around on our drawers. So that helps. Uh, you want to use an efficient, whatever, exposure time. I mean, there's no substitute for exposure time, really. Uh, I can take direct, you and I, with a 12-inch telescope, can take direct images of a 15th magnitude star in a matter of just a couple of minutes. But it'll take several hours if you get most of that starlight through a slit and then spread it out across the width of a chip. I don't know if that's answering your question.
Yeah, sort of. So you still use the same type of camera, but you got to have some kind of slit or some kind of apparatus in front of it, do you?
Yeah, well, you have that spectrograph thing. You focus the light from the telescope onto a slit, which blocks out everything else other than the star you want to take the spectra of. You can use no slit, and this RSpec thing that Gary was mentioning, that thread-on thing. There's no slit there at all. It's called slitless spectroscopy, and I showed an image of Campbell's hydrogen star. Every star in the image had a spectrum spread out to the left of it in that image, and so it's a great way for doing survey work, or was, because you not only your target object but everything else in the field, you can see the spectrum of it. And hey, that's a weird looking star, let's go and look at that. So there's opportunity for discovery. But really, to do a better job, you want to isolate the light from your star. So you stick it through a slit that gives you black backgrounds, and you use a collimator to catch the light expanding from the slit to the other side, make it parallel, bounce it off a grating or stick it through a prism, focus it back down again into an image of a slit. But this time that image is going to be a many slits, one for each wavelength in the light that's being illuminated at slit. And that's how it's done. You put a camera chip at that focused image, and you wait. Like that image I showed of the Orion Nebula, that's 800 seconds. Use it with an 11-inch telescope at the time. So that's what, 12 minutes of exposure time for something that I can take a picture of in just a few seconds, direct, because you're spreading the light out over many pixels.
Okay, great. Any other questions before we move on? If not, thanks a lot, Chris, and that was great. Okay, so Next, we have Robert with the sky this month. So I'm going to stop sharing and invite Robert to share his screen and run us through the sky this month. You good with that, Robert? There, is that it? Can you see it?
Yeah, I can see it there, but
Okay.
I can't scroll it, of course, right?
Yeah, just
So-
tell me what to do.
Okay, all right. So there's our usual image of the sun with its singular large sunspot that's rotating out of view now over the next couple of days. I guess it'll be gone. And I think Randy may have had an image of that recently that he shared with us, if I'm not mistaken.
Yeah, I think so.
Yeah, and continuing on in our planet roundup, as usual, you see that the green indicates the possibility that we can observe those planets, and the table differs a little from the usual ones over the past year, in that I have some notes in there about maybe when you can see it, or if it's difficult or an easy object, easy solar object to be able to, solar system, sorry, object to be able to see. And of course, the URL links, which are quite useful. And so I invite anybody to have a look at that. And if there's ever such thing as a clear sky again, maybe you'll be able to see some of our planets. Continuing on, we have the moon, and right now it's sitting at 1 day old, so just past technical new moon, and so it's, if we had the clear sky, we would have lots of opportunity for darkness, and therefore be able to do some deep sky things. We shall see what happens over the coming days. And I couldn't find any comets of, there's plenty of comets up there, but they're all exceedingly dim. So you wouldn't really be able to see much of a tail on it unless unless you have a fairly large scope with a long focal length and a really good camera. And then finally, the next meteor showers, we can all see there is the Lyrids coming up in April. And then continuing on from there, we have our binocular and deep sky objects, which are placed, it's just a list of what is some of the brighter objects that are well placed at this time of month. And continuing on from there, just a couple of planetarium screenshots. I was trying to plot some of the objects that have been recently gotten by a couple of our members in the very short window of opportunity that we had a couple of days ago. But it's an exceedingly tiny planetarium screen, so I'm afraid that I won't be able to really point you in any direction with regards to where they are on that particular screen, so you'll have to forgive us for that. And so there's an easterly view, and then it's followed by a westerly view, or southerly view, I'm sorry, and then finally the westerly view in our sky. If that was full size on your screen, you'd be able to certainly pick out some objects, but they're static. So and you can't, if I turn it on to have all the deep sky objects show up, then the screen becomes uselessly busy. So I have been looking for a planetarium program. I haven't had any success thus far whereby I can selectively showcase just particular objects, especially those that have been imaged by our members. But I haven't had any success in finding a planetarium program whereby I can actually do that without actually getting into copying and pasting, which is a very slow, it's not the way to do it. So hopefully there are a couple of more programs that I haven't been able to get installed yet, and maybe I'll get lucky with that. But outside of that, thanks for your patience and staying with the hobby, given the winter opportunities or lack thereof. Let's hope it changes soon.
Okay, thanks. Let me get this working again.
If no, Robert, if you don't mind my mentioning, and I ran across this completely by accident on space weather just the last couple of days. Somebody is looking at a flare-up on a comet. It's become 5 magnitudes brighter. It's, I think, probably still a long exposure thing, but
Is that B2?
Yeah, it's gone from hopeless to,
Yeah.
on a clear night, you'd probably be able to take a picture of it.
I think
Oh, is that right?
it's still 12th magnitude, I think, though.
Well,
Yeah.
if you have a big...
Sun Gao B2, I think.
I'm not sure. It's
It's
on
just-
space weather.
I think it's
Yesterday and the day
just
before.
passed us yesterday or the day before.
Oh, yeah.
No, this... okay. I'd have to check. It was on space weather yesterday and the day before. Looked like
5
a little
magnitude.
spiral.
Yeah, that's quite a lot of brightening, but still guaranteed that if indeed 5 magnitudes brighter is 12th magnitude, then it's still a difficult subject for.
No, I think
the
it was 12th before it outburst.
Okay, so if it's 5 up from that, then it's if we had a bit of sky, and if it's actually in our sky.
It's in the
That's
southern
right.
sky, yeah. I was looking at it on the Seastar app, and it's up for most of the night. B2, yeah. Can you see that?
No, but
But southern sky?
Yep.
Oh,
so like as in south northern sky. You're not talking about the South America now, right? Are you?
No, it's quite high. It's like 45 to 55 degrees high in the
What's it
south.
close to, Randy?
What constellation is it in?
I can't tell. This map doesn't show.
Yeah.
Okay.
It's in the south to southwest sky.
Yeah, well, certainly the comet URLs that's shown on the sky this month is a darn good place to go and look for it.
Yeah.
Okay. Thank you very much, Robert.
Yep.
So Gary, as I said, Gary's going to tell us about the Alpine Valley. So there's the picture, and take it away, Gary.
Thanks, Mike. Yeah, the last time I talked about the nice dark lake, which is called Plato, someone said, how come you didn't mention the valley? And so I figured, yeah, why not I take in the valley? The Alpine Valley, you'll see it splits the mountain range, the Alps mountain range, which ranges from 1.4 kilometers to 2 kilometers high. So as you're going down, just down, you'll see it. It's shaped like a V, very easy to pick up. It's one of the number one things amateurs pick up right away when they look, because it's such a cut, and it looks like it connects Marie Imbria to Marie Fergusus. I can't remember what name.
For your Taurus, is it?
Taurus. Okay, thank you.
Something like that.
Okay. Now, this usually valleys are created by water, but in this case, this was a volcano happening type of thing, and it went to full length. It ranges from 155 kilometers, and one paper I've read is 180 kilometers. So it depends on type of thing. It's 15 kilometers wide and 500 kilometers, 500 meters deep, type of thing, which is interesting. And right at the beginning, where you see the black mark right now, they're called the Guardians. They're just the rock piles type of thing. They're called the guardians. On a clear, good sky, and I remember I've seen it once when the jet stream was below St. John's, and I was using the 12-inch out in Butterpot. I could see the reef, which is a crack that goes to full length. Usually they're round and circular, and they're only about you can only, with your telescope, see things about a kilometer wide. But because this thing goes to almost the full length of the thing, 155 kilometers, you can actually see it, and it really goes. And actually, it's a volcano where the lava was going through it, and it's collapsed down. So it's actually, once you look at the surface here in the valley, you can actually, when you see the reef, it's about 2,700 meters below, I guess what you'd call moon sea level type of thing. So that is a really good thing to go look for. It's easy to see, and it's excellent to look at. And the best days for it is when the moon is 7 days old, 8 days old, 9 days old, and 21 and 22 days old. And over that, you'll actually see the shadow change, and you'll see more and more detail. It's a fantastic thing to look for, and it's beautiful with the naked eye. And when I'm using the cameras now, you can pick it up much better type of thing. It is a wonderful thing. Take it in. Now, if you go further down to the edge of this photograph, you'll see a crater with the one up from that.
That one?
Yeah, that's Cassini. That's 58 kilometers wide. It's often called the snake eye because of the two inner craters give it the impression that it's a snake looking at you. And on a nice clear one, you can actually see ripples where the mouth is. It's really good. And actually, Cassini is named after Cassini, the astronomer, of course, but he was the one who first saw it actually and reported on it, which I thought was kind of cute because usually you're just named after astronomers, but he actually was one of the first to report on that crater. So taking that crater, it's usually, most people miss it, but it's a really nice crater, and it has some nice riffles in it that haven't collapsed like what you've seen in the valley. And I think I've spoken too much about that, but that's a nice section of the moon to go explore and take your time. And actually, the best times to see that detail would be day 7, day 8, and day 21 and day 22. It's the same 2 days that you're looking at the valley. Perfect days to look at both those things. Any questions?
Yes, Gary, can I ask a question about the valley?
Yes.
Is there, do you have any information on what would have caused that valley in the beginning? I know it's full of lava.
By lava from the
volcano.
From the center of the moon. Okay.
Oh, so it's like a fissure.
Yeah, sort of. But what is interesting is, it's kind of interesting. Yeah. It's a bit higher than the marine imbrium. So, same with the Cassini one, a crater.
Yeah.
That's 300 meters higher than the floor. So it actually overflowed in and didn't fill out the, killed all the rays from the two big stars and the craters. All the rays that would come off it have all been filled in. But that is actually 300 meters higher than the base of the sea, Imbrium Sea.
Okay.
Gary, here's what I saw. Can you see that?
Sort of.
Yeah.
That's
Oh,
with the
so that you imaged that.
that's with the sea star.
Oh,
Yeah.
good.
Oh,
Yeah. So it's so much detail you can see, and it's enjoyable. I've finding that using EAA now improves my images of looking at the moon and of the other things than just looking at them with my naked eye. So I've sort of been going through both. Anyway, I hope that inspires you to take a look at the moon and find out and type of things, and yeah, enjoy yourselves.
Okay, well, thank you very much, Barry. And I suppose other people could have a Crater of the Month too, but I'm quite happy to keep hearing from Gary until he runs out of craters, and I suspect that's going to be a while.
But if anybody wants to talk about their favorite crater, go for it.
Okay, thank you very much. Okay, member observations. Surprisingly, we have lots of images from just a few nights, and some of them are lots of images of the same thing. There are a few images of the sun, so January 25th with that was with a Coronado PST, and this was Kim. This was February 3rd with this was with your Dwarf 3, is that right? Yeah, must be.
Yes, it was. Yes, the Dwarf 3.
Yep.
Yes.
And lovely sunspot group. And so this was Chris using the hydrogen alpha the next day. So seeing some of the texture there. And Randy had a try with, now he didn't call this first light. This might have been your first picture with the C-Star S30, but we won't officially call it first light. But there's the big sunspot 4374, and
They're both there. Yeah.
and the other one is there.
Yeah, you have to zoom in to see it. I was set up in my driveway, and it gave hints that it was going to clear off, but it never did. And that was amongst the best I could get for through the clouds.
Okay, well, that's something anyways. And so Kim did a picture January 23rd of the moon, a little bit after new moon. And then, so that was with her iPhone, and then used the DSLR to get a much more detailed image.
Yep.
And then this was, would this have been your first light with the Dwarf 3?
Yes, I believe that was.
Yeah, so there you are, iPhone, DSLR, and Dwarf 3, and very sharp, lots of detail there. So congratulations.
Thank you.
All these new instruments is probably why we're having a snowstorm tonight, but and this was after this is the same image, I guess, with some processing in I guess Stellar Studio comes with the Dwarf
It comes
3.
with the, yes, that's the main, and then I just do a bit of sharpening and denoising with Lightroom.
Yeah, so very nice. That's pretty good for a first shot with a telescope. And Jim Johnson did an image of Plato, and I guess that the valley is just off to the edge of this image, so you can't quite see it. But Jim, is this another new telescope?
No, it's the one I had last fall.
Last fall. Okay, well, that's still newish. But very nice. Maxitov. And another one
lovely.
with the Dwarf 3. This is another one of Kim's with very sharp, lots of detail here. And January 29th, so the day after Jim's. Marcellus has been doing our the full moon setting in the morning because he's got the view of that. So this one was from February 1st. And then we have a bit of a festival of Jupiter. So there's Io off to the right, this January 25th, January 28th. There's Io, and January 28th was when the shadow went across. So a couple of us were imaging that nice red spot there. And this is also with the Maxitov. And there you can see the shadow, and I think Io must be right there, but a little harder to see. A nice red spot. And this is a GIF now. There we go. So this is Jim's animated GIF of the red spot and the shadow of Io moving across. And I was looking at Jupiter the same night. So there's Io and Europa over here and Ganymede here, the red spot. And then it's got this kind of unattractive yellow cast to it. And Chris taught me or pointed out that I was missing a little box in the planetary image preprocessor program that can stretch it to look white. So this is this one was at 952. This one's at 956 with Io a little bit closer, and it looks a little more white. This one's still with the old processing, but there is the shadow of Io in the red spot. And this was my attempt at an animated GIF. And then Chris, February 4th, nice image of Jupiter. And that's where I learned about this stretch histogram white to 75%. And Tim and Sue, that was the same night. Must have been almost the same time, because that feature seems to be about the same place with the Celestron 9.25. Yep, and Io's in about the same place. Here's Io. And Robert did Jupiter and all the moons. So top to bottom, it's Ganymede, then Io, and then Callisto and Europa. And Kim, again, this always astounds me that you can get a picture like this with a handheld camera, the bands and the moons. And
I know, crazy, isn't it?
That's some kind of black magic there. I don't understand it, but it's amazing. Very nice. What lens did you have on that? That was
800 and 800
that's your 800
on a full frame. Yeah.
You don't have gorilla hands, do you, Kim?
I know.
Well, we've discussed that before, and I think
Lots of practice with the warblers at great distance.
Yeah, we're not going to have an arm wrestling contest and let Kim in. That's very impressive. And then another Jupiter just a couple nights ago, through the clouds. That was kind of a frustrating night. The petals got, there was lots of excitement about auroras a couple weeks ago, and the petals got, it was just a few days after the meeting, and the petals, not surprisingly, were the ones that actually got the pictures. So this is from Torbay and Flat Rock. Lovely shots. And thanks for those. And this one, this I guess was not officially Kim's first light for the Dwarf 3, but it was the first picture through the Dwarf 3, so I thought I'd throw that in.
Yeah, that was a pano attempt.
Yeah, well, that's cool too.
Yeah,
but I think you've got other cameras that can do that.
absolutely, and far better quality. But again, it's just getting used to it, right?
Yep. And Kim, people probably heard, and we saw that we're just past a new moon, and that's when you may get a solar eclipse. And there was one yesterday, but it was in Antarctica, and not even Gary went there. So, but to celebrate that, Kim sent us her pictures from almost 2 years ago. That's hard to imagine that was
Yeah.
almost 2 years ago, but we hadn't seen those before, so I thought I'd throw them up here. So, and Kim was down near Port aux Basques, right?
Yeah, well, just Cape Ray, basically.
Okay.
JT Cheeseman Park is right at Cape Ray, just down
Okay.
the coast from where you guys were.
Well, I wasn't. I was
Oh.
like an idiot. I was in Gander, but from where
Okay.
Randy and Robert and people were. So
Okay.
some pictures, I guess, from before, and using a filter sort of put together with some other filters on the DSLR, and then some different images of totality. Kim, you want to say anything about what's going on here?
No, there's like I did a little bit of darkening, but black point adjustment just to bring down and tighten up the ring around the clips. But I was pretty impressed when I kind of got back home and looked at my images on the computer that I'd actually managed to pull it off, because it's the first time I've ever done anything like that. So it was to see it was one thing, but to capture it was something else.
Yep, very nice. So thanks for sharing those and reminding us of 2 years ago. And so there are a few deep sky objects this month. Some of them were reprocessing. Some of them were newer images. So Robert sent in a picture of the Cocoon Nebula. So there's Cygnus, the Cocoon Nebula's down here, and
that was from a while back, though.
Yeah, that would have been from the summer to see, but so you were testing something out. Well, I guess it was just that there was no sky and you hadn't processed this one yet.
Right.
Yep, very good. Okay, and that's fair enough. And the Crescent Nebula, Robert revisited this. We saw it from the summer, but Robert revisited it and used Cyril to remove the stars, do the stretch on the nebula, and then put the stars back, right?
Yes, correct.
Yep. So that's
first time for Cyril for me to complete it.
So I don't know if we have something equivalent to First Light for processing package, but that's what that is.
Yeah.
Okay. John Peddle found the Intergalactic Wanderer. It's a globular cluster. It's associated with the Milky Way, but it's a long way out, farther out than the Magellanic Clouds. And there it is with the sea star. Very nice. Then Gary did the Rosette Nebula. So there's Orion, the Rosette Nebula, and the satellite cluster. The cluster is sort of lighting up the gases in the Rosette Nebula, and that's always a lovely image. But you had to work hard on that one, 114 minutes. Oh, and it's a mosaic. Is that, Gary, is that two pieces? Is that a two-piece mosaic, or you're muted? You muted, Gary. Oh, there you go.
Trying to get out. No, actually, that's like about 15
Oh,
going around. Yeah.
so that's impressive how the sea star can stitch all that together. And oh, that's why it's 114 minutes. Okay.
Yep.
Okay, very good. Very nice. And then there were lots of images around here. So this is oh, there we are. The belt of Orion and close to so Mintaka, El Nilam, and El Natak, and we have the Flame Nebula and the Horsehead Nebula, and the bright gas behind the Horsehead Nebula is a dark nebula. It's dust, and the gas behind it is IC 434. So that's the emission nebula behind the Horsehead Nebula. So we've got some pictures of the Flame Nebula and the Horsehead Nebula, and of course, this time of year, several pictures of the Orion Nebula, which has a very active star forming region. There's also the Running Man up here, and so we'll run through them. So Robert did the Orion Nebula. There it is. And the bright area here, it's the star formation region. And I did the same thing and got the Running Man as well. And Tim Carrick and Sue Hart got a close-up of the trapezium. So those are the 4 very young stars that are washed out in most pictures of the Orion Nebula. So very nice work on that. And I did another one of the Orion Nebula on, excuse me, February 4th. Oh, I'm going backwards. Hang on here. There we are. I've used up. Okay, so this was the sort of official first light for the Dwarf 3 for Kim, and this was again the Orion Nebula. And then Randy also had a first light. He now has a C-Star S30 Pro, which maybe we'll hear a little bit about in March. And so he did the Orion Nebula. You can see it's a wider field.
That's a nice picture. That's a nice picture. I like that.
And the Flame Nebula and the Horsehead Nebula. And for comparison, there's Gary using the S50 for the M42 and the region around Alnitak. So interesting comparison. And that's it for the observation reports. So I'll just remind you that our next meeting is March 18th, and we're looking for a bunch of short talks. We have a couple lined up, but there's room for more. Getting to be time to start sending in some images. You don't have to wait for a clear sky. The level 1 stellarium, it's now time to register if you're interested in that. I was going to say about the Terra Nova. Oh, I think I did say that there are still some service tent sites. I don't think there's any Authentics, but you should let them know they're still working on their schedule. And I think that's it. So thank you, everyone, and take it easy tomorrow when you're shoveling, and be safe.
Thank you, Mike.
That's it.
Thanks, Mike.
You're welcome.
Good show.
Welcome, everybody.
So Cynthia now is going to have to eat 3 boxes of cookies because I can't eat 3 boxes of cookies. So Cynthia is going to sacrifice herself on behalf of the group. Oh, they are in the freezer, so she doesn't have to.
There you go.
Today.
I was going to say they can freeze well.
Right. Okay, well, good night, everybody, and take care.
Take care.
Good night.
Right. Thank you. Good night.
Cheers, guys.
Thanks, Mike.
We can only
Thanks,
hope.
guys.
Good night.
Good night.
Okay.
All right. Catch you later. I'm gone.
Okay, good night.